Hello, pre-algebra students. This is Mrs. Urano, and this is our lesson on section 10.4. This is the last new section in our book that we are going to cover. In the next class on Tuesday, we will be doing a review of Chapter 10 and then taking the Chapter 10 test and then doing a review of the entire class before the final. So, before we get started, I just wanted to remind you about this sheet of paper that you have here that I had you print out a little while ago. You can always print it out again or just take a blank piece of paper and write pre-algebra questions at the top. But this is my strong tip to you for how to study and prepare for the final. So throughout Chapter 10, if you have questions, or throughout the review, the warm-ups, the lessons, anything that comes up that you're like, oh yeah, shoot, I forgot how to do that long division thing, or oh yeah, I forgot about rational numbers, or oh yeah, I need to practice this or that, or I need to ask a question about something, just jot it down here. Use the backside if you need to as well, but write it down, and then when you get your questions answered, you can cross them off, and this will be a great study tool for you. It will also help you know what questions to ask during office hours if you attend, so that you can get your questions answered and be prepared and learn the material. So keep that nearby all the time, even if you're doing homework. If you're not sure about a homework question, you can even copy the question down here. Don't just write like number 5, but write enough of the questions so that you remember specifically what it is you want to ask. Okay, then the first thing we're going to do really quick is page 5 of some old notes that you had. So all the notes in this section are numbered, and this chapter 10 are numbered starting at 1. So go back to page 5, and we're going to do this problem really quickly as a review of Venn diagrams. So remember, Venn diagrams can sometimes partially overlap, sometimes completely, sometimes they don't overlap at all. If you have two events that don't even overlap at all, then those are called mutually exclusive, because they can't, it's impossible to have both of the events occur at the same exact time. We also have a complement of an event, where if one event would be snowing and there's a 22% chance of snowing, then the complement of snowing would be the probability of not snowing, which would be, if the probability of snowing was 22%, the probability of not snowing would be 78%. The probability of not snowing. So anyway, we talked about a number of different things like that. Just wanted to review that briefly. But now we're looking at a scenario here. Out of 500 students, so this is the entire sample space. I'm just going to write 500 here just to remind myself of that. Out of 500, 156 of them study Spanish as a foreign language. So I'm going to go ahead and write Spanish right on this line here. That's what this circle represents, that they study Spanish. And I'm also going to write in parentheses 156. Normally when we write the exact number, it's in parentheses. And then percentages we usually write more inside. Of those studying Spanish, this is very important, of those studying Spanish, 1 out of 6 also study French. Now we have 500 students altogether. If 1 out of every 6 of these 500 studied French, that would be a lot. But that's not what this says. It's 1 out of every 6 of these 156 students. So when you divide 156 by 6, you end up getting 26. So that means 1/6 of those 156 students is equal to 26. So when we look at the students studying French, we'll write them here, and there's 26 students that study actually both. Now it doesn't tell us how many students maybe study French but don't study Spanish, but this is what information we do have, that we do know. And the question is, what fraction of the students study both Spanish and French? So we know that 1/6 of the Spanish speakers also study French, but it's asking what fraction of the students. So the implication is of the total number of students, which is 500. So we want to know that 26 out of 500 students altogether, that's what we want to know, that study both. So 26 out of 500 is our question. We can reduce it to 13 over 250. We can reduce it even farther than that if we wanted to. Anything else? 13's prime. So we could go ahead and do a calculator. I actually don't have my calculator with me right now. Oh, maybe I do. I can use this one. So this ends up being equal to 0.052. But it asks what fraction, so we can just leave it as this fraction here. So that would be 5.2% of the total students study both Spanish and French. So we could put 5.2 in here. Percent. All right, but anyway, we've answered question 2. There's more we could do here, but we're just going to focus on answering the questions that are written. The next question says, if a student is selected at random from those 500 students, what is the probability that a student who studies both Spanish and French is selected? Give your answer as a decimal. So probabilities can be written as a percentage or a decimal, and in fact, we already answered that question. The probability would be 0.052 as a decimal. All right, excellent. So moving on, we are going to look at the lesson for today, which is in section 10.4 of your book. And the thing here is we're really going to look at defining the sample space of all the possible outcomes. And we're going to have some kind of interesting situations where we're going to have to figure out, well, what are all the possible outcomes that could happen here? And we're going to use tree diagrams and also kind of a table to figure out what all the possible outcomes could be. It's not quite as straightforward for some of these. All right, so let's look at this first situation here. A couple would like to have 3 kids. What are the various possibilities for the genders of their kids? So maybe they'd have all 3 boys, all 3 girls, or a girl and then a boy and then a girl. So there's a variety of different possibilities. We want to know what all of them are. And we're going to use a tree diagram to model this. So what I recommend you doing is looking at the space that we have here and take it and kind of do a little dotted line halfway through. So we have half on top and half on bottom. And then we're also going to do 2 lines here to split it up into 3 columns. So I'm going to kind of do it like that and like that. This is just going to help you use the space well. And so we're going to look at the first kid here. And the first kid could either be a boy, I'm going to write a really nice big B, or a girl, a nice big G. And this is how we're going to do our tree diagram. We're going to kind of branch off. Now the second kid, if the first kid's a boy, then the second kid could either be another boy or it could be a girl. And same down here, if the first kid's a girl, then the second could either be a boy or another girl. I'm always writing the B on top just to make it a little systematic. And then when we get down to the third kid, if they've had a boy and then another boy, the third kid could be another boy again, or it could finally be a girl. Or in this case, again, the third kid could be a boy or a girl. If this has been the route, it could be a boy or a girl, and a boy or a girl. So this is our tree diagram, and what does this really mean here? Let's take a look at this. So there are really a variety of outcomes here. This node up here at the end, we have 1, 2, 3, 4, 5, 6, 7, 8 nodes. So the total number of equally possible outcomes is 8 here. And this is going to end up going in the denominator. I'm going to write that up there right now briefly. All right, so what this kind of node right here means is that they started with the first a boy and then another boy and then another boy. So that's what that right there means. It means BBB. And we're going to write that down here. That's one possible outcome, 3 boys. Another possible outcome represented by this node is that they first had a boy and then another boy and then a girl. So this represents BBG, right? Another possibility represented here, we're just going to keep going down, is boy, girl, boy, B, G, B, or boy, girl, girl. So those are all for the possibilities for if there was first a boy. Now we're going to keep going because there's a chance that first it was a girl. So I'm going to write all those here now. It could have been a girl and then a boy and a boy. It could have been a girl and a boy and a girl. A girl and a girl and a boy. Or a girl and a girl. All three girls. So you might have been able to kind of generate this yourself in a different way, but this is called a tree diagram, and it's a very helpful skill to have to be able to use tree diagrams. I'm going to just comment right now. I think it's in your homework problem number 8 that I highly recommend doing a tree diagram because it's talking about flipping, if it's flipping coins and it's heads or tails, or if it's answering a true-false question. This is a really helpful model to use to try to figure out what the entire sample space is. So we have 8 possible different outcomes, and what is the probability of each outcome? Well, there's only one outcome that's boy, boy, boy. So that's one outcome out of 8 possible total. Boy, boy, girl is one outcome out of 8 total. This is another outcome out of 8 total. So you can see for all of these, they're just one outcome, and there's 8 possible total outcomes. So the way we do probability is the number of favorable events over the number of total events. So we can see the probability of all of these outcomes is equally likely. They all have a probability of 1/8. So if we go and look at the probability distribution bar graph. So this is a probability model where the first thing is the outcome and then next is the probability, and that's pretty standard for a probability model. But if it asks you to do a bar graph for the probability distribution, then that's what this is going to look like here. We would have a bit of a kind of a graph here. I'm going to leave a little space here to label. So the first possibility would be boy, 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 or boy, boy, girl, or boy, girl, boy, or boy, girl, girl. And I'm just going to put, you know, there's going to be 8 total. So I'm not going to make you write all of them out, but we're going to get the idea here. All of these have the exact same probability. So when we make all these bar graphs, they're all going to be the exact same height because there's equal probability for all of them. And this actually is very important. That one looks a little higher than this one. Sorry, I didn't mean to do that. But they all have a probability of exactly 1/8. So if we label this, then this would be, this axis here would be the outcomes. And then this axis here would be the probability. And I've labeled 1/8 there, so we're good. This is the probability distribution bar graph. And since these all have exactly the same height, since all of these numbers are exactly the same, we call this something special. We're going to write it down here. We call it a uniform probability model. Uniform, think when you wear uniform to school, everyone dresses the same. Uni means one. A unicycle has one wheel on it, right? So this is one form. It's all the same form, the same height. So the word we're going to write in the blank is that the outcomes have equal probability. Equal, same, 1. So an example would be something like this right here where they all have the same height. Another example would be when you're rolling a fair die. So any number has the exact same probability of being rolled. Or when you're flipping a fair coin, heads and tails both have equal probability of landing. So there's quite a few things like that that have equal probability for if you're spinning a spinner that has the same exact size all around it. Now, there's also something called the non-uniform probability model where the outcomes have different probabilities. Makes sense, right? Probably would have guessed that. Or another way to say that is that there's variation in their probabilities. They're not all the same. They're not uniform. There's a lot of examples of this in real life, but we're going to look kind of at one modification up here. Let's see where I want to go next. First of all, let's look at some specific events. So this is the probabilities laid out here of each individual outcome. But let's say I want to look at an event that is the event of getting exactly 2 girls. So the probability of the event of getting exactly 2 girls. Okay, that's what we're going to look at here. And so the probability is always equal to the number of favorable events over the total number of events, which is 8. So how many of these outcomes are favorable to exactly 2 girls? No girls at all. Only 1 girl. Only 1 girl. Exactly 2 girls. There's 1. 1 girl. 2 girls. 2 girls. And 3 girls. That's not exactly 2. So there are 3 outcomes favorable to exactly 2 girls out of 8 total. And those outcomes are boy, girl, 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 boy, girl, or girl, girl, boy. So it makes sense in a sense. If there's 2 girls and there's 1 boy, and the boy can either be first, or he can be born second, or he can be the baby of the family. Right? It's another way to think about it. Or another specific event, what about the probability that they're all the same gender, right? Some people want to have 3 kids and you wonder, are they all going to be the same gender? Well, remember there's 8 total possible outcomes that goes in our denominator. And how many outcomes have the same gender? Well, in this outcome, there's all boys, so that's 1. And then in this outcome over here, there's 2 all girls, so that's 2. There's 2 possible outcomes that have all the same gender, which reduces to 1 in 4, or 25%. Now, I want to just mention really briefly that if a couple already has a boy, and then they have another kid, and they have a boy again, when we're looking then at the probability that they're going to have a 3rd boy, it is no longer 1/4 anymore. Or it's not even before all 3 boys, but it was only 1/8. They have already traveled down this path. So this is just a brief mention for something that might come up in future statistics classes or something. But once you've already had 2 boys, the probability that they're going to have a 3rd is what? Anybody? It would be 50%. Because there's a 50% chance they're going to have a boy and a 50% chance they're going to have a girl. Unless you have some crazy theory that in this family, like for generations, there's just always been boys and it's not actually an equal 50-50 probability chance. But for the most part it is. Okay, so let's go down to here. We've talked about this a little bit before, but if the event is the number of girls, then we can talk about the probability that there'll be 0 girls, 1 girl, 2, or 3. And we actually already talked about how the fact that the probability of exactly 2 girls, that there's 3 outcomes favorable to that. So the probability is 3 in 8. So that's nice. What about 3 girls? There's only 1 outcome favorable to that, GGG. So there's only 1 there. So the probability of that would be 1 in 8. How about 0 girls? Well, the only outcome favorable to that would be boy, 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 which is only 1 outcome. So that's also 1/8. But let's examine a little bit more closely the outcomes that would be favorable to only 1 girl. Well, either that girl could be born first, or the girl could be born second, or the girl could be born third. So there are 3 outcomes favorable to that, and so that means the probability there is 3/8. So look at this now. If I were to make a bar graph around this, where this axis was the number of girls, we could have 0, 1, 2, or 3. The probability of 0 or 3 girls is kind of slim. That's only 1/8. So I'm going to make this line right here, 1/8. But now, up to here would be 2/8, and up to here would be 3/8. So the probability of having 1 girl or 2 girls, and thus 1 boy, is actually quite a bit higher. So this here is a perfect example of a non-uniform probability model. There or there we can see that the probabilities are different. So that would be non-uniform. Cool? So If you decide you want to have 3 kids, these are your chances that you might end up with all of the same gender or that you might end up with different numbers of genders. Okay, moving on, away from genders. We're now going to talk about rolling dice. And to simplify the situation, we're going to talk about rolling 2 dice that have 3 sides. Is that even physically possible? Not really. But we're going to simplify it down to only 3 sides to make it a little bit easy for us now. Now, some of you might know, actually, normally dice have 6 sides, and there is actually one sum that comes up most frequently, and at least theoretically is more probable when you roll 2 6-sided dice. Do you guys know what it is? It's actually a 7. So let's see, I won't get into that one now, but let's look at 2 3-sided dice. And in order to look at this sample space, there's a couple of possibilities. I'm going to use the tree diagram first. And we're going to look at the first roll could either be a 1, a 2, or a 3. And then the roll on the second dice could be a 1, a 2, or a 3. Or say the first one was a 2, the next one could be a 1, or a 2, or a 3. Or even if the first die was a 3, the second die could be a 1, a 2, or a 3. So these are our possibilities. We can see when we count the end nodes here that there's actually 9 possibilities that we could roll. Now, for this particular type of situation, I actually prefer using a chart to represent this. So I'm going to do a chart like this. I'm going to make a little square with some space. And up top I'm going to say that the first die could be a 1, a 2, or a 3. And then on the side the second die could also be a 1, a 2, or a 3. So you can see here there's 9 possible outcomes. And this outcome would be a 1 and a 1, or a 1 and a 2, or a 1 and a 3, right? And this would be a 2 and a 1, a 2 and a 2, or a 2 and a 3. And then filling out the last column, a 3 and a 1, a 3 and a 2, or a 3 and a 3. All right. Give you a sec to catch up there. So we're going to look at certain events, and the events are the sum, that the sum of these 2 dice might be 2. We can never have the sum be 1 because the lowest that each die could be is a 1. If this is a 1 and this is a 1, they're going to sum to 2. So in fact, that's an outcome that's favorable here to a sum of 2. Or they could sum to 3, 4, 5, or 6. Now the only way we could get 6 is if it was a 3 and a 3. So there's only one possible way we could sum to 6. So getting a sum that's so low or so high, both are equally improbable. So there's only one way we could do that out of all 9 outcomes for each of these here. A 3 or a 4 is or a 3 or a 5 is a little more common, working towards the middle. A way we could get a 3 is a 1 and a 2, or a 2 and a 1. Those are 2 ways we could get 3. Ways we could get 5 would be a 3 and a 2, or a 2 and a 3. So there's 2 ways we could get 5. But now let's look at how many ways we could get 4. A 1 and a 3 makes 4, a 2 and a 2, or a 3 and a 1. There are 3 different ways we could make 4. So the probability of a 4 is actually the highest out of all of these. You see that? This is most likely. What I like about doing a model like this is that we can actually see here that these are the answers that sum to 3. These are the answers that all sum to 4. They happen to be along a diagonal. These 2 answers sum to 5. And then this is the one answer that sums to 6. And this is the only answer that sums to 2. So it's kind of neat how the sums all end up being on diagonals there. Let's see, I can do an arrow there for 3s. And we can see, in fact, that the diagonal that's the longest, well, that's one thing I really like about this model, this diagonal here is obviously the longest out of all of these diagonal lines, and this is the one that sums to 4. So it confirms our earlier findings. If we looked at this bar graph and we had the 2 and 3 and 4 and 5 and 6, I'm going to just write them right underneath. The axis here, it could be labeled the sum of the 2 dice. And then on the y-axis we'd have the probability. And this is 3 times as probable as these. So I'm going to make this as far as I can do it. Go. And then this is going to be 2/3 as big. And then these are just going to be 1/3 as big. So it's symmetrical, you can see. But when I label this axis, I'm going to label this 1/9, 2/9, and 3/9, which of course reduces to 1/3, but I'll leave it like that. So there's my probability distribution bar graph, and this you can see is non-uniform. That's the word we used. All right. Let's see, we've got another situation down here where I just want to briefly again talk about using a rectangle chart. This can get really funky, but if we have this systematic way of representing possible outcomes, that's where the power of math is here, that this systematic way of representing them can make a kind of trickier problem really straightforward, actually. So in this situation, we're looking at a situation where we're wanting to develop a model for the sum of a 7-sided die, whoa, 7 sides, numbered 1 through 7, and a 3-sided die numbered 4, 5, and 6. Okay, so let's do the 7-sided die this way, because this is longer. And let's do the 3-sided die this way. It could be a 4, a 5, or a 6. All right? See how we did that? Okay. And now what I'm actually going to write inside here, rather than writing the sums like that, is I'm just going to write the total. So if I rolled a 1 and a 4, that sums to 5. A 1 and a 5 sums to 6. A 1 and a 6 sums to 7. So go ahead and pause this really quick and fill in the rest of the squares. Okay, welcome back. So what you should have noticed is something that looks like this. Did you notice that along your diagonals? There's only one way to get 13. You had to get the highest number on both dice. There's only one way to get 5. You'd have to get the lowest number on both dice. But actually there's 3 ways to get 7 and 3 ways to get 8, 3 ways to get 9. So it's kind of interesting there. So if you were a betting person, then any one of these answers would have been equally likely. However, on a normal die, which is 6-sided, 1, 2, 3, I'm just going to draw this really quick. You don't have to. You can see, applying the same idea, that the diagonals, especially if it's a square, there's only one main diagonal. If it's a rectangle, there'll be a couple. But you can see it's going to be this big diagonal that's going to be the most probable sum to be rolled, which is a 6 and a 1 making 7, a 1 and a 6 making 7, or a 5 and a 2, or a 3 and a 4, 4 and 3, 2 and 5. So you can see that 7 really is the best bet to make for rolling a sum on 2 regular 6-sided die. Let's see, do we want to talk about, yeah, so I'm also just going to mention the total number of possible outcomes would be all of these rectangles, so there's 7 and 3, so there'd be 21 there. And if we wanted to talk about the specific event of rolling a sum of 6, for example, then the outcomes favorable to that would be a 2 and a 4, or a 1 and a 5. And so the probability of that would be 2. There's 2 possibilities out of the total 21 possibilities. So not very likely. Another specific event could be the probability of a sum that's greater than 9. So why don't you go ahead and try to fill that out yourself and pause really quick. All right, so there's 21 total possible outcomes. That goes in our denominator. And how many sums are greater than 9? Notice this is not greater than or equal to. So the 9s don't count, nor do any of these numbers up here. But there's 1, 2, 3, 4, 5, 6, 7, 8, 9. What a coincidence. There's 9 possible outcomes that would give me a sum that's greater than 9 out of the 21 total. And to reduce, when we divide by 3, we get 3/7. Would be the probability of getting a sum that's greater than 9. And we'll just leave this part blank for now. I think we get the idea. Okay, let's go into our last page. This one's kind of cool, where these are two really important things. One of your homework questions is going to be very similar to this. I think it's question number 6. So we can write even that here. This is like homework number 6. And I think homework number 8 was the one that I recommended doing a tree diagram really similar to this one here. So you can write homework number 8 here if you want, just to help you out there. Okay, so this Battleship one is just kind of fun. Hopefully you all know how to play Battleship. You have a board like this where with letters A through J, which those is actually 10 letters there. And then the numbers 1 through 10, that's obviously 10 different numbers there. And so you have all these squares here, which is actually 100 squares total, and you place your ships there. So you have a carrier that has 5 holes on it, and so maybe you place that one here, 1, 2, 3, 4, 5, that's your carrier. And then you have a battleship with 4 holes. You have 2 ships that have 3 holes on them, and then the destroyer can hide really well somewhere because the only way to hit him is to hit one of those 2 squares, which is least probable. So let's talk about that here. The probability, the outcome of hitting a destroyer. Well, there's only 2 holes there. So there's only 2 ways you could possibly do that out of all 100 squares. So that is not very likely. The outcome of hitting a cruiser or a submarine, they both have the same size of 3, so they're going to have the same probability. On your very first guess, the probability of hitting one of those is 3 out of 100 squares altogether. So only 3 out of the 100 squares have a cruiser in it. Only 3 out of the 100 squares will have a submarine in it. But a battleship has 4 holes, so that would be 4 out of 100 would be the probability of hitting it on your first guess. And a carrier, that's the one you're most likely to hit, which would be 5 out of 100 probability. Of course, some of these reduce, but we're just going to leave it like that for now. Now, there's one other possibility, one other possible outcome, because we're going to have all of these that are going to end up adding up to 100% because we're going to look at every single individual outcome, and there's no overlapping here. So the other big possibility is that you could miss, right? So what's the probability that you miss? Out of 100 squares, how many of them are empty? Well, let's do a little quick math here. There's 5, 5, and 7. So that would make 17. There would be 17 squares that have a ship on them. 17 squares with a ship. And there's 100 squares altogether, so that means there would be 83 squares with no ship. So 83 out of 100 is your probability of missing on your first guess. Now, something interesting to note about this is after you make your first guess, say you guess B7 and there's no ship there. Of course, I haven't placed my others. Here's my 3-er, here's my 3-er, and here's a 4-er. All right. So now that I've made I've missed, I can go ahead and guess again. But now there's only 99 squares left. So I have a slightly greater chance on getting it my next time. Let's say I'm like super unlucky and I end up missing over and over and over again. I just can't hit a boat for my life. Now, actually, the probability of getting a boat my next time is increased because I've already eliminated a lot of scores where they aren't located, right? And of course, it's interesting because once I hit a boat, let's say here, and I actually make a hit, woohoo! Now the probability of getting a hit on my next turn is actually much higher because I'm going to guess to the left or to the right or to the top or the bottom of this to try to get more of that same ship. So that's kind of interesting. But you'll notice that all of these probabilities end up adding up to 100 over 100, which is 1, or written as a percentage, 100%. And what type of probability model? Is this uniform or non-uniform? It would definitely be non-uniform. All right, kind of fun. I like that game. Last one for today. Are we ready? This is going to be a short lesson, definitely less than an hour. All right, so we have some data below that show the heights in centimeters, that's our unit, of 25 tomato plants. All right, in our garden. So what we're going to want to do for here is we're not going to want to have 25 different columns with every different possible outcome that's listed here. What instead we're going to do is group them into intervals. So this is actually on page 287 of your book, and it's just a guided practice problem. But they tell us to group them in intervals from 80, and they actually say, I'm just going to do 80 to 90, 90 to 100 by tens, 100 to 110, 110 to 120, so go ahead and write these down as well. And you can pause if you need to finish writing that, if I was quicker than you were. But now, let's go ahead and look. We're going to very systematically, and a lot of students get stuck with doing this too fast and not kind of crossing off their numbers, but we're very systematically going to go through and tally the frequency of a plant occurring within this range given our observations here. So, first point is 100, and I want to point out again, I've mentioned this before and it says it in your book, but 100 is right on the border between these two buckets. But we are going to count it always in the higher bucket. So technically this is actually like 90 to 99 or to 99.99 if there were decimals and fractions involved. But we usually still just label it 100, and we always actually put the 100 above. So I'm going to put that there and cross it off. 124 goes in this bucket. 86 is in the 80s. This is in the 110. So again, it's right, it kind of straddles these two, but I'm going to put it there. 90 straddles but goes in the higher one. 96 is definitely there. 82 is in the 80s, and so on and so forth. I'm going to be quiet as I do the rest, and you can do them as well. When I get to my 5th tally mark, I do it diagonal. Let's see if I make any mistakes. I think I've got it. All right. All right, so you can see our frequencies here. I'm actually going to write the numerals now. And then the probability is the frequency over the total number of plants. So we're going to have 4 over 25 for these, 7 over 25, 3 25ths, 5 25ths, which also reduces to 1/5, and 2/25. Okay? So this is our probability distribution. And then lastly, we're going to practice writing it as a histogram. So again, I just want to emphasize, we call this a histogram instead of a bar graph because these are continuous, these are intervals, it's a continuum here. So we're going to have our, let me not write that there. We're going to have the height, and our unit is centimeters, and that's going to go at the very bottom. We're not going to go all the way down to where the height is 0, so we're just going to start with the height being 80. So I'm just going to do a little kind of jagged line here, which means we skipped something. Okay, so we're going to go 80 and 90 and 100 and so on. Okay, and then they don't occur above that. And then on the y-axis here, what is the y-axis? It's the probability of picking a plant that has that height. So, the last thing that might be helpful is to rewrite these as decimals, but I'm actually just going to leave it as a fraction, and that'll be okay. So, we're going to go anywhere from down 2 up to 7 of the 25ths. So I'm going to make 7 25ths at the top, and then let's see, 6, 5, 4, 3, 2, 1. Good, I did that pretty well. 1 out of 25, 2 out of 25, 3 out of 25, 4, 5, 6 out of 25. All right, that's really hard to read, but I told you what it says, so you know what it is. All right, and both the 80 to 90 and the 90 to 100 range are both at the 4/25 probability. So that's how we do that there. The next range is 7/25, so that's the highest probability according to this sample here. 3 would be a little lower than the 4s. Now don't go down to 1 because of this numerator. It's still 5/25, so that's more common. We're going to go up to here. And then lastly, just 2/25. So I have my histogram. I've got my bars. They are touching. My intervals are labeled. My axis is labeled. My numbers are labeled here, and the axis is labeled. So that is a stellar histogram. I guess the only thing that might be better is if I kind of had like dots here maybe. We don't normally do that. Oops, nothing's at the 1/25, but I could potentially have like little lines that came across or something, but yeah, this is not necessary. But some of them have that. Okay. All right. So go ahead and use your notes to, you can complete the homework since we finished early, or you can just wait and do that on Monday. But put your notes in your notes section so you know where to find them, pages 9 to 11. And you can put page 5 back where that belongs. And good luck, students!